Hello everyone, and welcome to this deep dive into understanding autocorrelation and its interpretation. This video is designed for anyone working with time series data, from financial analysts to data scientists, who needs to understand the underlying patterns and structure in their data. By the end of this video, you'll be able to identify trends and seasonality and better inform your predictive models. Let's start with the fundamental question. What exactly is autocorrelation? Autocorrelation measures the correlation between a time series and its lagged values. Think of it as how much a data point is related to previous data points in the same series. If a variable is autocorrelated, it means that its past values actually affect its current values. This relationship is crucial for understanding the dynamics of your data. Autocorrelation is a powerful tool used to detect trends, seasonality, and even the underlying structure for statistical models, like AR terms and ARIMA models. While specialized software can do this automatically, it's incredibly insightful to understand how to perform autocorrelation manually, especially in a common tool like Excel. Let's walk through an example. We'll demonstrate the step-by-step process for calculating lag1 autocorrelation in Excel. The first step is to create a lagged series. If your original sales data is in column B, you'd create a new column, say C, where each cell references the previous row's value from column B. This effectively shifts your data by one period. Next, you use Excel's built-in Correl function. You'll apply it to your original sales data and your newly created lagged sales data. This formula will output your lag1 autocorrelation value. Once you understand the concept for lag1, you can extend this to build a complete autocorrelation function, or ACF table. To calculate higher lags, you simply repeat the process. For lag2, you'd shift your original series by 2 rows and then apply the Correl function again. This can be extended for any number of lags you wish to analyze. After calculating several lags, you can then build an autocorrelation table, which lists each lag and its corresponding autocorrelation value. Plotting this as a bar chart is a powerful way to visualize the autocorrelation function, or ACF, and quickly spot patterns. Now that you know how to calculate it, let's talk about how to use this autocorrelation output to interpret your time series data. If you observe high autocorrelation at lag1 that slowly decays over higher lags, it's a strong indication of a trend in your data. For example, if your ACF values are 0.9, 0.8, 0.7, this suggests a strong positive trend. Seasonality is revealed by significant autocorrelation at specific lags. For instance, if you have monthly data and you see spikes in your ACF at lag 12 and lag 24, this strongly suggests a 12-month seasonal cycle. Let's review an example and some important notes to keep in mind when interpreting autocorrelation. Consider an example where your ACF shows a gradual decline from lag 1, combined with significant spikes at lag 12 and lag 24. This pattern would indicate both a strong trend and clear seasonality with a 12-period cycle. Remember, autocorrelation values always range from -1 to +1. A value close to +1 indicates a strong positive correlation, and a value close to -1 indicates a strong negative correlation. To judge the significance of your autocorrelation values, you can use a critical threshold, often approximated as ±2, divided by the square root of n, where n is the number of data points. Values outside this threshold are typically considered statistically significant.